Hello, this is the lecture on signature biometrics. So signature is not a very important biometric in comparison to others that we have seen. Fingerprint and face recognition in particular are the two most important biometrics by large. Signature is much smaller in importance, but anyway, in some scenarios, it's the only applicable. For example, there are many cases in which we have handwritten information and then a biometric comparison or a forensic comparison must be performed. So we can find some cases, even popular cases in the media, where signature has been of very important relevance to solve some cases. For example, here the previous president of the Community of Madrid was demonstrated to have faked his master's degree, and that was demonstrated by examining signatures in the documents related to the master's degree. So as I said, signature is small but is growing. So as other behavioral biometrics related to handwriting, speech, actions, behavior, gait, movement, interaction with a smartphone, all these behavioral biometrics are growing in importance relatively with others. We can see this trend between early 2000s and more recent year that signature and related biometrics have grown dramatically from 2 to 10%, 5 times. So, and that growth is the biggest one in all biometrics compared. And this is because the behavior nowadays is of main interest in profiling people and in extracting biometric information for identification or for other tracking purposes, for analyzing the health state and other information that can be useful and can be extracted from that behavioral information. So signature is small but it's growing. It's really important. There are other behavioral biometrics like keystroke biometrics, gait biometrics. We are not going to see all of them. So I selected signature. We selected signature because it's kind of representative of all the other behavioral biometrics. The techniques behind signature biometrics are similar to the techniques for feature extraction and for matching that you can find in speech, in gait, in all these dynamic signals. Signature is a dynamic signal, and as a dynamic signal, the methods to extract features and to match features are similar to all behavioral biometrics. So you can see this lecture as representative not only for signature, but for all behavioral biometrics. So a signature is basically the act of signing. We sign in a paper on a device, and this has been used as a legal means of verification, of identification for many years in notary public, legal documents, and so on. So if we want to recognize or to verify signatures automatically, there are several challenges. So it's not an easy task to be performed automatically, especially because signature as a behavioral biometric has large intra-variability. So we can see here, for example, two input biometrics, two biometric samples, two signatures from the same person. And you can see that the visual aspect and also the dynamics around the signature, velocity patterns, pressure patterns, can vary a lot. There can be big differences between two genuine samples of the same person. So that is high intra-variability. It will be the task of a good feature extractor and a good matcher to be robust against that variability. And at the same time, when we compare a signature of a given person to signatures of other people, we have a special case here, and that's when the other people, the other person we are comparing in this kind of imposter matching has some information about our signature, and then the imposter fakes our signature, fools our signature, imitates our signature based on the amount of information that he has. He may has some information about the shape of the signature, about the dynamic of the signature. Perhaps he saw us just over the shoulder when we performed our signature someplace, or he has access to some written signature on a paper, and then he tries to falsificate, to fake the signature. So imposters may have some information about us, and then they may use that information for attacking our account. These kind of attacks are also present in other biometrics. We saw some examples of presentation attacks in face. An impostor can generate a mask and then present the mask in front of the sensor in a kind of presentation attack. This is a kind of presentation attack. If an impostor uses some information about the attacked account to generate a false acceptance, then he's doing a presentation attack. And presentation attacks in signature are of very special importance. Why? Because these kind of attacks are very easy to perform. A presentation attack in face, presentation attack in fingerprint, it's very difficult to perform, very costly, and always in security we have this kind of cost-benefit trade-off. So in signature recognition, it's very easy and it's very cheap to perform this kind of imposter attack. Then usually the systems are evaluated, and in terms of accuracy, against this kind of skill forgeries, a forgery of the account, against this kind of skill forgeries, and also against other subjects, in what we call random forgeries, or just normal kind of imposters, which don't have any kind of information of the attack account. So biggest challenge for signature and for all behavioral biometrics: high intra-user variability and perhaps low inter-user variability, depending on the amount of information of the attacker, and depending on also the individual at hand. We may have other individuals that behave similarly, even if they are not attackers. So we have here an example of written signature. Genuine is the first one, and then two cases. So what do you think is a genuine and a fake? So it's difficult to tell just by looking at the shape of the signatures. So correct answer is like this. This is a genuine one, the same subject, and this is a skill forgery. So this is another subject that is trying to attack, to mimic the signature of the genuine client under attack. So for signature we have two main approaches. Offline, this is basically using the image of a signature. This is image-based signature. This can be used, for example, for check processing, when we have scanned documents with signatures and we want to compare or process those signatures automatically. And then the second big block is online signature, and this is where we have also dynamic information about the signature process. So this is image, this is kind of signal kind of processing, and this kind of signal processing is similar to the signal processing in speech, in gait, in any kind of biometric generated time sequences. We're going to focus on dynamic signature verification. For offline, nowadays for biometric processing, biometric recognition of static image signatures, we can use similar approaches compared to face. So based on deep learning applied to these image signatures. So CNN's approach, convolutional neural networks, but adapted to the specifics of the signature. So we are going to leave this out with this presentation. You can think of it as variants, modifications of image-based biometric like face, using general deep learning approaches for both segmentation of the signatures and detection and recognition of the signatures, similar to what we saw in face. And then the big difference is here in the processing of the dynamic signals, which is similar to the processing in speech, keystroke, and so on. So now let's concentrate on dynamic signature biometrics. Applications. So you can see login to user accounts, payments, different places like points of sale, e-banking, different kind of transactions. Also in legal transactions, legal documents, e-government applications, parcel delivery, many applications, any in fact application where we have a kind of touch screen and we can interact with that touch screen, and then we can sign on that touch screen. Now let's see the systems. The main stages are the same always of a typical pattern recognition system, and in particular a biometric system. So we will have acquisition first. If it's a verification, then we will have an identity claim. We will have a database of role models or templates. If it's a verification, then we compare just with one pre-enroll model. After the pre-processing, we extract features, template, we compare one-to-one, we generate similarity or distance. In this case, this is similarity. We normalize the score, perhaps. We apply a decision threshold, and then we accept or reject binary decision. So let's see the data acquisition and pre-processing. This is an example of signature tablet, the one that is commonly used in like banking applications, postal service, that you will see now in many different places. So you can see that a dynamic signature is captured. So information generated by these kind of devices, these are specific for signature, specific in terms of the hardware. For example, the time resolution, the sampling rate of the touchscreen, the space resolution is designed for proper acquisition of signatures. So, and the output of the acquisition process is like this. So here we are showing an example of a signature. And then the three functions here, horizontal is a time axis in time samples. So you see here around 400 time samples. We have in this particular model 100 time samples per second. So this is around 4 seconds. This is synchronized in 3 channels. This is horizontal position versus time, vertical position versus time, and pressure versus time. So you can see, for example, that the horizontal position is growing since the beginning, is growing more or less until the half of the signature, until half time of the signature. And this means that we are growing from left to right. So horizontal position is growing. And then more or less half the position, horizontal position goes almost from the maximum value to the minimum. And that's because from the maximum horizontal position to the minimum is because we are doing some kind of flourish, like this, and then go up and then continues growing. That's because the second half of the signature. So you can see that analyzing this horizontal vertical position, we can really describe the dynamics of the signature. And then we have also the pressure. Not all the devices generate the pressure. In this case, this kind of signature tablets and also some smartphones nowadays can also generate a pressure indication. So you can see, for example, that when we are pressing, so pressure is different to 0. When pressure is equal to 0, that's because it's a pen up. In a pen up, pressure is equal to 0. So it's good that you can read these kind of plots. In fact, in the signature lab, we're giving you some signature examples generated with this kind of devices, and you will see these functions. Devices now where you can generate this kind of dynamic information are many. In fact, any touchscreen device, so tablets, smartphones, even there are dedicated pens with this kind of signature signals are generated automatically using accelerometers and gyroscopes. So any kind of touchscreen based or accelerometer based devices where we can write. After we capture these signals, sometimes there is, not always, but sometimes there is kind of a pre-processing to clean the input samples, to filter the input samples, to normalize the input samples, is a kind of pre-processing. In most of these devices, the trajectory points are sampled regularly in time. So this means that if we are slow in some regions, then we will have more points, more sample points. If we are fast in other regions, then that means that the spatial separation will be larger. And then depending on the approach afterwards that we want to use to compare, sometimes we need to resample that. So that depends on the approach. Signature recognition is not like iris, where we have like a standard iris code and a standard procedure. There are many different implementations. Some implementations may work with these regular time samples. Other approaches may work better with samples spaced equally in the space. So that depends. So this can be a step that can be applied or not, depending on the approach afterwards. You may need to resample or increase the samples or eliminate some samples or filter some samples to eliminate noise and so on. This is particularly important in cases where we capture dynamic signals in smartphone touchscreens, where there are because you can see here that the trajectories are very clean. In a smartphone, trajectories sometimes are not so clean, so perfect. So we have some like deviations over the smooth stroke because the interaction with the touchscreen, and because especially if the input is not a stylus but the finger. If we use the finger, we will find trajectories that are much noisier. The noise will be much higher in the acquisition, and we will have to filter that, to filter out that noise. So after we generate the time sequences, clean the time sequences, normalize, resample if needed. Sometimes, depending on the system, we may have to also normalize the time frequency, especially if we want to interoperate between different devices. We want to compare a signature capture with a smartphone and compare it with a signature capture with a digitizing tablet or a signature tablet. Then we may need to also resample the frequency to make those two sequences compatible. And then we may also normalize in position with respect to the center of mass, or in order to align the outer boundaries. We may need also to rotate, so all signatures are rotated to have the same principal axis, for example. So spatial normalization in terms of position, rotation, size, and time frequency may be also important before extracting features and before comparing. Then after this pre-processing, we go to feature extraction. So there are two main blocks or group of methods for feature extraction. Global features. In global features, basically a full signature, a whole signature composed of 2, 3, several time sequences. The whole signature is described as a whole with a multidimensional vector, multidimensional holistic vector. Information inside that vector can be composed of a number of physical elements of that signature. Let's say feature 1, signature duration, feature second feature, average velocity, third feature, number of pen-ups. So you can see that we have individual features, real numbers or integers describing different aspects of the signature, and we may have a large number of these features. So and a feature vector composed of that represent the signature, the given signature. Also, we may have a deep network that generates an embedding or a representation without any physical meaning, like this one. So we may also use a deep network that acts as a global feature extractor, and then we train that network, deep network, to generate the best global features to represent the signature. But this application of deep networks to generate discriminative global features, like has been done in face. In face, we have excellent deep networks like BGG face that we saw, that generate an excellent global feature representation of a face. We don't have that for signature. This is something that is currently under research. So the best global feature representations published and known and used commonly in applications are these kind of global features composed of features with physical meaning, like that. And then on the other group of methods are, instead of one signature, one feature vector, it's representing a signature by a series of feature vectors, like by a sequence of feature vectors. So this is not completely eliminating the time dimension. So we may represent the signature also by the x, y coordinates across time or across stroke or across segments, or other kind of representation that is also variable with time. So either a global feature or a time representation of the signature. So this is an example of a representation of a signature, the different time functions. In this case, the input digitizing tablet is x, y, and pressure over time, and also two additional functions. These two additional functions are the angles of the stylus over the pen tablet. So if we have a pen, some pens, some stylus over the tablet, over the plane of the writing plane, will generate two different angles. If we have the stylus completely vertical, or we have the stylus that it's horizontal or more horizontal with respect to the plane, these angles will vary over time. The angles of the pen with respect to the plane of the tablet or of the writing plane. But these two angles that have been demonstrated to be very unstable, so they are mostly not very useful for biometric purposes, not very stable with the people. So typically these two time functions, the time functions related to the angles of the pen across time, they are not used usually. In fact, they are not used in this representation. So only x, y, and pressure are used in this representation. And this is a global feature for one signature composed of 40 features. First one is duration, number of pen-ups, number of changes in the strokes, jerk, which is the derivative of the acceleration, standard deviation of acceleration in vertical position, and so on. So we have many different colors here is because the different features were studied in different works. And this way we can represent one signature, for example, by 40 numbers, and these 40 numbers are very representative, are very distinctive of that signature. In fact, we can use those 40 numbers to compare signatures using any kind of distance, simple or sophisticated distance. A kind of time sequence representation can be like this one. We have this is also an example of the second kind of feature representation based on time sequence. We have the input signature represented by these 5 functions. We don't use the last two, they are not very useful. We just concentrate on the first 3. This is raw data from the sensor, and then what we do here is to generate an extended set of time functions based on these 3 time functions. So you can see, for example, that the first 3 are exactly the same from the raw data set, x, y, and pen pressure over time. Here x sub n, the n is a time index. So we have x coordinate versus time. It's exactly the same. So x, the full function x is 1. Full function y is 2. Full function p is 3. And then we add additional functions. For example, path tangent angle, path velocity magnitude, the radius of the curvature, the magnitude of the acceleration. So different functions that are computed based on the first 3. So this is a kind of extension, additional data extracted from the raw data. And then once we have this additional data, we have represented the signature, and then we can use a model to represent all this extended set of data. There are several studies comparing which are the best features in signature. For example, in this case study that we perform at UAM in the framework of a European project, we compared in a large data set, including around 1,000 people, state-of-the-art devices, comparing different features. So you can see here, for example, in this plot, equal error rate in that benchmark. That was the Biosecure project, that benchmark. So you can see that for signature verification in that benchmark, only using X and Y, the information trajectory, in a time sequence representation with the matcher was based on hidden Markov models, we will see afterwards. When we introduce also the pressure, then you can see that the error rates were significantly reduced, so better system. Then by including these gamma and theta vectors, these are the angles of the stylus, then the errors increased. So we discarded these angles, and then we introduced additional data. This is the path tangent, which is obtained based on the X and Y trajectory information, velocity, and others. So only these two, the angles of the pen with respect to the table, are the ones that really they corrupt the results, they degrade the performance. So we leave them out, and the others, as we introduce additional data to our representation, and this is the full package of time functions and their derivatives over time, then we can reduce the color rate to around less than 1%. This is excellent results. Excellent results in comparison to just using the trajectory, because we are modeling also the dynamics in terms of trajectory, acceleration, curvature. All these dynamic characteristics of the trajectory, the signals, are the ones that really have the power to discriminate between different people. And this is similar to what you will observe in speech, in gait, in other behavioral biometrics. Not only the raw signals, but some additional dynamic information that you can model and that will improve your verification, your biometric results. In top, you have this is equal rate, and then you have these DET curves, the corresponding DET curves. You don't have to really study this. It's only a representation and give you the flavor that including additional information, dynamic additional information in our template really improves the performance of behavioral biometrics. So we have seen very briefly pre-processing techniques, how to extract features in a global feature vector in an extended set of time functions, and then let's compare our features. So that depends. If we have a global representation, then we will compare two global features using distance measure. So you can see if we have global features, we will have some kind of distance classifier. We can have basic Euclidean distance, statistical Euclidean distances like Mahalanobis, or other kind of statistical or any kind of really classifier. We have a fixed size classification problem, so we can use any known classifier, general classifier, working with fixed size features. We can use GMMs, we can use neural networks, we can use super vector machines, we can use anything. And there are several studies comparing most of them. As a result, the research shows that the most important thing is not really selecting a sophisticated matcher, is selecting a good set of global features, a set of that is representative, distinctive, and stable across time, that can work well with the intra-variability of the subjects. For example, the set of features that I showed before, based on 40 features, which are selected and studied and carefully selected from previous research. On the other hand, if we represent the signatures with time sequences, then we can go and process those sequences regionally instead of processing locally each time event, we can kind of post-process those templates, perhaps integrating the information in strokes or in temporal regions or in segments, temporal segments, and then apply a comparison to those segments, segment-to-segment comparison. Or we can just leave the time functions or time features as they are, and then apply a local matching, like an elastic matching that compares the full function without integrating the function into small parts. And for that, for both approaches, either segment to segment or point to point in time. Here, remember that we have here time sequences. So point to point means time point to time point, and this is temporal segment to temporal segment. So we can use techniques to match temporal sequences, like hidden Markov models or dynamic time warping, or variants of dynamic time warping or hidden Markov models, which are standard techniques in pattern recognition. This is an example of when we have global features. We can use just for comparing two global features, global feature X, global feature Y, Euclidean distance, global feature X against M, where M is a representation of a subject. M will be the mean of that subject, and that subject will be also represented by its variability. So a subject will be represented, in this case we use Mahalanobis distance, by two things: the medium, the mean vector M, which represents the mean of the templates corresponding to that subject, and the matrix sigma. Matrix sigma represents the variability around the mean in that feature space for that particular subject. So that subject will be represented by a mean vector and a variability matrix. And then the distance of an input template X against the model, mean and sigma, will be something like this. This is the Mahalanobis distance. So you can see that a subject here is represented not only by a specific global feature, is represented by a statistical model, M and sigma. And we will have to construct M and sigma based on a number of reference or enrollment templates. So this incorporates a kind of statistical information about the variability of the subject. And that's because when we have enough information from the subject, we model the variability of the subject with this sigma, and this improves a lot in comparison to Euclidean distance. We are modeling the intravariability of the subject. This is very important in behavioral biometrics. So this is also a distance-based, but incorporating statistical knowledge, statistical information that we estimate for a particular subject, depending on the enrollment templates that we have. The more templates that we have from a particular subject, the better will be the statistical estimation of sigma, and the better will be this distance, this dissimilarity that is used to compare in our matcher. So this is, I think, an excellent example of how to introduce here statistical modeling in a distance comparison. And this statistical model really represents for each subject in our database the variability for that particular subject, which can be very different. Some subjects may have very stable signatures, short and compact signatures, and others may have long signatures, very variable in time. And we have to really model for each of them what is the variability, the typical variability of that subject. When we have time vectors, the two main approaches are DTW, dynamic time warping, or hidden Markov models, or variants, like extensions of DTW, like deep learning based DTW, or some variant of DTW including some kind of statistical modeling. But the core is using some kind of dynamic programming, dynamic optimization to match elastically the two time sequences. So you can see here the idea. we start here, so we're comparing two signatures, not in this space, of course, this is just the visual representation. We compare the full set of time sequences, the full set of 18 time sequences that we have before, the full set of 18 time sequences, but at the beginning, and we compare to the full set of 18 time sequences in the beginning. We establish some correspondence based on an optimization criteria, and then we are running, comparing, and establishing some restrictions to that matching locally, and that's DTW. That it's like going from, this is a representation of the time for the input sequence, time for the output, or the sequence that we are comparing. We are comparing sequence J with respect to sequence I. This is I and J, sequence J, sequence I. These two sequences we are comparing, and we are trying to find the best path that aligns the two of them. And then using this best alignment path, we can establish the similarity between the two signatures. This is done in speech, in gate, in any time-based matching of time sequences. And on the other hand, we have hierarchical models. In this case, instead of going locally, time sample by time sample, we are kind of integrating different temporal regions in states. So let's say we're having here like n states, and can be just 2 states, 4, 10. So, and these states are usually designed heuristically based on experiments on a data set. And there is a structure. We can jump from state 1 to 2, or stay in the same state. Perhaps we can jump a different state. So this represents kind of the structure of the signature. And when we are in one given state, we observe some of the functions here. So we estimate this model for a particular signature, or a set of signatures and Roman signatures, and then we use that to generate what is the probability that that model trained for a particular subject generates an input signature. So this is kind of a statistical modeling and a statistical matching. Performs really, really well when we have a large amount of training signatures. Performs really, really well when we have just one signature for training, for characterizing a subject. In fact, most successful schemes and commercial schemes that work operationally in open conditions, they use both. When you have only one signature to represent 1, 2, 3, very few signatures to represent a subject, they use DTW, and then they switch to hierarchical models when they have 5, 10, 15, 20 signatures to model the user. And in the intermediate step, before switching, sometimes they use both in combination with different weights. So most of the two of them are very important in signature, and the same gate, keystroke, speech, and so on. So just a representation of what performance you can expect. This is also some experiments that we conducted here at UAM. This is a database, very difficult database, because there was it was captured across 15 months, more than 1 year. So in the biometric comparisons, we compared between reference template, the comparisons between the reference template and the test were separated several months. So there are several months between training and testing. So there's a kind of big time lapse between training and testing, and this is a challenge for really signature and any biometric. Different experiments. So you see here performance against skilled forgeries. So imposters here are imitating signatures. Random imposters means we are comparing different signatures. Two different approaches, DTW, the fusion, the combination of the two, and the different experiments tell us the amount of training signatures, 4 training signatures per subject, and growing until 40 signatures per sign. So the more information we have for a particular person, then the better is the statistical modeling that we can do, especially with this statistical models. So you can see, for example, for skilled against hard imposters, in the statistical modeling, we're going from kind of low performance. This is error rate, almost 15% error rate, equal error rate. So the more signatures we have to model the user using a hidden Markov model, we can go down to 1% equal error rate, just hidden Markov model. But for just 4 signatures, DTW work better. This is typical when we compare statistical methods versus optimization elastic matching methods when we have short sequences. But the best performance for DTW, for dynamic programming, when we have a large number of signatures, is this error is much larger than this, because DTW cannot really exploit this increasing information statistically as an HAMM. So the improvement as we increase the amount of training data is bigger for a statistical HMM modeling. And then we can combine both. So you can see less than 1% error rate when we use both of them at the same time, less than 1% against imposters. And similar things happen in against random forgeries. Challenges in signature. Signature is still very active, so there are still limited results when we interoperate, when we compare signatures captured with digitization tablets versus signatures compared with smartphones. So more robust features and more robust or better pre-processing steps need to be developed in order to deal with several sensors, especially when we sign with the finger instead of a stylus. Some people use like very short signatures or very low quality signatures, so the universality is limited in signature. How to deal with problematic signatures is also a topic of research. How to incorporate signature to mobile devices, how to protect and secure signature, because signature is very sensitive information, and additional topics, not very really important. So this is just a representation of some of the challenges in mobile application of signature, which we think it will be very important in the future, especially because payments using a smartphone. The area here is limited, the ergonomics are different, the naturalness of the writing process is not the same compared to using a stylus over a tablet. So the screen is not that familiar, so the way we sign is affected by this small touchscreen area. There are also computational limitations, sampling limitations. So this is a kind of engineering challenge to really implement signature biometrics in smartphones. There are some developments, but not really successful commercial products yet. And that's all in the signature lecture. Thank you.